welcome to this talk on quantum computing for big boys and girls. So as you can probably tell from the title, this is a public audience talk, which means that I'm going to assume no background in even computer science for this talk. So this talk is appropriate for anybody from, say, high school up to computer science degree, let's say, but doesn't know anything about quantum computation. If you're looking for more hardcore details about quantum computation, this is unfortunately not the right place for you. Okay? So my name is Sevad Ghoribian. Most people just call me Sev, which is the first three letters of my first name. You should know where your information is coming from, so just a little bit about me before we begin. I did my PhD studies at the University of Waterloo in Canada, my postdoctoral studies at the University of California, Berkeley, and I am currently a junior faculty member at the University of Paderborn in Germany. Okay, so before we begin, obviously we're talking about quantum computers. This talk is going to be based on quantum mechanics, right? And we're going to find out what quantum mechanics is, but just to sort of set the stage, I like to use this quote by Richard Feynman, which goes, "The paradox is only a conflict between reality and your feeling of what reality ought to be." Okay, and so as we'll see throughout this talk, one of the key things about quantum mechanics is that nobody really knows how to make sense of it in some sense, and in order for you to really accept it and move on and use it, you kind of have to give up what you think of as what reality is, what you're used to in your everyday life in some sense. Okay? But all in due time, we'll get there. Let's begin. This is going to be the outline for the talk. And like I said, this is a talk for big boys and girls. Okay, so what that means is that I'm not going to treat you like little boys and girls. I'm not going to treat you like children. It's going to be slides. I'm not going to have lots of fancy animations or anything like this. Imagine you're sitting in a university lecture hall, and I'm going to treat you like responsible human beings, if you will, right? So we're going to start with beginnings, right? Why do we care about quantum computers? Then I'll tell you a little bit about the theory behind how they work, a little bit about applications, and finally I'll try to tell you a little bit about experimental realizations, okay? And out of all these four topics, this is the one I realistically know the least about, so this should be taken somewhat with a grain of salt, but I'll try and share with you what I know. Okay, so for the record, I'm a computer scientist by training. Okay, so let's begin with the beginning. Why quantum computers, right? So anytime you embark on any sort of task, right, especially difficult one, such as building a quantum computer, we should ask, why? Why are we doing this, right? What is the payoff? And there are a number of reasons actually, but I'm going to give you two for this talk. And one is going to be from an engineering perspective, and the other one will be from a computer science perspective. So let's begin from the engineering perspective. So the first reason I want to give you is that of shrinking microprocessors. So in this picture, I have a microprocessor, and it's about this big. And what makes this thing compute, roughly speaking, is sitting on that microprocessor are millions and millions, by which I mean over 100 million to give you a sense of scale, tiny, tiny little transistors. And that's in what sense allows us to compute. And the more transistors we fit on this chip, in some sense, the faster the chip can compute. And that's exactly what we've been doing for the past couple of decades. That's how chips have been going faster and faster. And now if you think about this for a second or two, you'll probably come to the realization that, of course, any such shrinking process just can't go on forever, right? And indeed, what started to happen over the last decade or two already is that as we shrink things down further and further, the laws of physics start to change. Okay, in particular, what happens is that we go into the realm of so-called quantum mechanics. So let me demonstrate with an example. So right here I have a pen, right? And if I take this pen and I throw it in the air and hopefully catch it, right? The motion of this pen as it goes through the air is well described by a very old set of laws now called classical mechanics, right? Those laws have been set by Sir Isaac Newton a couple of centuries ago, right? Very well established, they work very well, except when we go out to the world of tiny, tiny subatomic particles. Okay, so when we start talking about things like atoms, for example, the laws of classical mechanics fail miserably at describing this world. And that's exactly what's happening with these computer chips, right? They've shrunk so much that we start to see quantum effects showing up in these chips. They don't really do what we want them to do. So if the laws of physics are changing at this scale, then the obvious first question is, well, why don't we just build a computer that's based on quantum mechanics to begin with? Okay, so that's the first reason I want to give you for building quantum computers. It's an engineering perspective. It's that we cannot keep shrinking microprocessors down forever. Okay. But I'm not an engineer, right? I'm a computer scientist, so I'm most occupied with computer science problems, right? And in particular, things like algorithms, right? And so the second reason I want to give you that's a bit more from a computer science perspective is that of the so-called factoring problem. Okay, so for example, if I give you the numbers 3 and 7, right, then it's very easy for you to multiply those in your head and get the number 21, right? So easy as pie, you probably learned this in grade 2 or 3. Okay, but I can also ask you the reverse question, right? If I give you 21, can you factor it back into its factors 3 and 7, right? And factoring is something you probably learned much later, right? You probably didn't learn it to at least high school. At least that was the case in my school system. And there's a good reason for that. We're going to get to that in a second. Okay, so, but suppose I ask you to factor 21 in this case. Well, sure, that looks easy. 3 and 7, 3 times 7 equals 21. But what if the number I give you to factor is this one, right? There's no way you're going to factor that in your head, indeed. And the hope is that a computer can do it. Okay, fine. So that's the factoring problem. Why in the world should we care about this, right? What's so special about factoring? So I'm going to provoke a discussion by asking you a question. Do you believe the following statement? So I claim that it's strongly believed that there is no efficient classical factoring algorithm, meaning there is no general purpose technique that works on all integers, if you will, that scales nicely as the size of the integer grows. Okay? So do you believe this statement? A priori, it's probably not obvious to you, but I claim that actually the truth is you probably implicitly have already consented to your belief in the statement, and let me explain why. I'm going to ask you what I claim is an equivalent question. Do you shop online? Okay, because when you shop online, you probably put in your credit card data, right? And what protects your credit card data, right? What prevents other people from stealing it? Well, crypto systems. We have crypto systems which take your data and scramble it basically so it looks illegible to somebody who's not supposed to read it. Okay? And the problem with crypto systems is, especially very standard ones like RSA, for example, is we've never formally proven that these things are actually secure, right? We don't know how to do that. The only proofs we have rely on an assumption, and the assumption is that factoring is hard. Okay, so if you believe that factoring is hard, then indeed RSA is secure. But if factoring were to be easy, then you would be able to break these crypto systems and steal everybody's money, right? And indeed, the twist in the story is that in 1994, Peter Shor showed that if you could build a large-scale quantum computer, then you could solve the factoring problem efficiently. Okay, so suddenly, in the mid-1990s, quantum computers become very, very interesting, right? Because everybody realizes in computer science that they're able to do something that classical computers seem not to be able to do. Okay? So in theory, quantum computers can break RSA, and here I really want to stress the words in theory because this is assuming you can build a large enough scale quantum computer. Okay? So this is the second reason I want to give you, that of solving the factoring problem, which in principle would allow quantum computers to basically break all these crypto systems that we currently use in practice. Okay. So that's all I want to say about motivations. Let me try and tell you a little bit now about how these computers actually work. Okay, and again, we're going to keep things high level. There's going to be no math or anything like this. And before we begin, I always like to start with this quote. Here's a picture of our good friend Einstein. And this quote goes as follows. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed that the moon exists only when I look at it. So what in the world does this mean, right? Like, how could the moon exist only when you look at it, right? And, what in the world were they thinking about at this time that even would cause somebody to ask these questions, right? And that's exactly what quantum physics is like. Okay, so 100 years after its founding, there's still an entire field of research called quantum interpretations that's essentially arguing about, what does quantum mechanics actually mean? How do we interpret it? But let me be clear, the math seems to work, right? So indeed, all your electronics that you have, like your smartphones, your desktop, etc., none of these would work if quantum mechanics was incorrect. Okay, so semiconductors require quantum mechanics to essentially be correct. Okay, so let's begin. I'm going to start at the beginning. Okay, so what languages do you speak? So presumably you speak English, right? You're watching this video. Perhaps you speak some other languages too. But what language does a computer speak? Well, it speaks binary, right? So the only thing a computer understands is ones and zeros. So here, for example, is a word in binary. And you might think this is a silly looking language, but actually anything you could say in English or any other language on this planet, you can say in binary and vice versa. Okay, so it's actually equivalent in power to everything else. Okay, so what that means is that a computer's memory stores sequences of zeros and ones, right? Every single bit, the smallest piece of information it can store, stores either 0 or a 1. Okay? And I'm really stressing the use of the word or here. Okay, so just a bit of notation here. You can ignore this notation if you like. Eventually I'm gonna use them to denote quantum states, but don't worry about what they actually mean. It's still bit 0, bit 1. If you really want a formal description, very briefly, this is going to be describing, it's a ket vector is what we call it, and it describes a column vector. Okay, so in quantum mechanics, everything is done in the world of linear algebra. Okay, but I'm not going to go there for this talk otherwise. So if a classical computer's language is just sequences of zeros and ones, then what language does a quantum computer speak? So a quantum computer consists of quantum bits. And the short form we give to this in the field is qubits. And the main difference between a classical computer and a quantum computer is that a classical computer can only store 0 or 1 in a single bit, but a quantum computer can store both 0 and 1 at the same time. So I want you to reflect on this for a second, right? Because what I'm saying here is actually extremely deep. Okay, not because I'm saying it, right? Because it, as far as we know it, this aspect of quantum physics is very deep, and this is exactly what we don't really know how to understand yet, right? So really this is like saying, the bit is both 0 and 1 at the same time, okay? So it's like me saying that, I have this pen and it's not here and it's not just here, but really it's in both places at the same time. Or you're sitting here watching this video and you're out grocery shopping at the same time, okay? That's what quantum mechanics predicts is possible, okay? And the way we denote this in quantum mechanics is we put this plus in between. Okay, so denote my qubit is in both 0 and 1 at the same time. If you like, here's a cute little picture where, I have two ducks. This is supposed to represent one duck in this picture, which is supposed to be essentially in superposition, right? It's in two different states at the same time. Okay, so the name we give to this is superposition. Okay, so you might think, of course, this is, of course, ridiculous. How in the world could an object be in two places at once? Okay, and if you think that, then certainly you were not the only one. And in 1935, Schrödinger gave a now infamous thought experiment known as Schrödinger's cat. Okay, and the way this experiment works as follows. You imagine that you take a cat, okay, and you put it into a box. Okay, so I've modified this image here to really stress that there's this black border here, because I want to stress that the box is closed. Okay, the box is not supposed to be open, so you can't look inside it. By the way, you're not supposed to do this experiment. This is not something you do at home, right? So it's a thought experiment. So you put the cat in a closed box. In the box, there's a vial of poison, a hammer, and some form of control mechanism that you can feed bits into from the outside. And the way this works is that if you feed a 0 into that control mechanism, then nothing happens. The poison is not released, and the cat's just happy doing whatever it's doing. But if you put in the bit 1 into this control mechanism, then the hammer falls, the flask of poison breaks, and the cat dies. Okay, so that's in the classical world. But in the quantum world, I just told you that you can set a control to both 0 and 1 at the same time. So what does that mean? Well, if we interpret quantum mechanics literally, it means that the hammer falls and doesn't fall at the same time, the flask of poison breaks and doesn't break at the same time, the cat dies and doesn't die at the same time. Right? Again, of course this sounds ridiculous, right? And that's precisely the point of Schrödinger's cat, right? It's supposed to demonstrate how crazy this seems from our everyday perspectives, right? Now, I'm sure, or at least I certainly hope, that in your everyday lives, you have not seen a cat that's both alive and dead, and you know how you would solve this in your everyday life, right? You would say, well, Sev, why don't we just open the box and see whether the cat is alive or dead? Good idea. And here, quantum mechanics is one step ahead of us because there's a phenomenon known as collapse. Okay, so to really explain this, before we open the box, right, let's describe the state of the cat as a superposition of alive and dead, right? It's both at the same time. Now, there's something a bit funny about quantum mechanics, which is that if I look at a quantum state, I necessarily disturb it. So I'm not going to claim what I'm about to say is the correct way of thinking about this, but the way I like to think about this, to try and make some sense of this, is that quantum particles are absolutely tiny. Okay, they're subatomic particles, like a tiny electron, right? And why should looking at this thing disturb it? Well, what does it mean to look at this thing? So one way you would observe this, for example, is you would shine light onto it, photons, right? And photons would bounce off this electron, and the electron is so tiny that just the mere act of being bombarded by photons is going to change its state, right? It's going to disturb it. So again, that's a very rough sense of how you might want to internalize this concept that just observing a quantum state changes its value. Okay, so what does that mean? That means that if we go back to our cat in the box, if I open the box to look at what's inside, what quantum mechanics predicts is that at random, meaning in this case with probably 50%, I'm going to find a cat that's either alive or dead. And importantly, once I see that the cat is alive, then in the future when I look at the cat again, what I see will be consistent with what I already saw previously, meaning the cat will still be alive, right? It's not going to switch states. Okay, so in other words, the state of the cat collapses to the cat is alive. Okay, and this is in some sense how we resolve this paradox. Okay, so you might be wondering, Seth, how do I know that this is actually true? How do I know that nature actually works this way? And you shouldn't take my word for it, right? You should take a physicist's word for it, who have done a very, very nice experiment known as the double slit experiment. And the best way, I think, to experience this experiment is to go watch this video on the internet, which I absolutely love. It's not my video, but it's aimed at kids, which makes it twice as good. What I'm going to do is I'm going to put a link here up top, at the top right, and I'll kind of pause. I'll stop talking for about 10 seconds, and what I want you to do is pause this video, go click on that link, watch the double slit experiment. Should be about 5 minutes long. When you're done, come back and we'll digest the video and continue the talk. Okay, so feel free to go click that link now. Okay. So if you haven't clicked that link yet, feel free to pause the video and do so. Otherwise, let's just briefly digest that video, right? So what that video showed is that, if you have a screen and in front of it you place a wall with two slits in it, if you will, and if you passed waves through this, right, then you had this interference pattern of many, many bars. And if in a classical world you shot, let's say, particles like photons, bullets through this thing, then you would just see a pattern of two bars, right? And what happens is when you go to the quantum world and you shoot a stream of, say, electrons, then you also see this pattern of bars, this interference, so it acts like a wave. But the relevant part for our discussion in particular is even when you shoot single particles through those slits, somehow they still seem to interfere with themselves to create this pattern. So it's the only way we can explain this is that the electron seems to be going through both slits at the same time and then interfering with itself. So it's in superposition. Okay, and just like we saw before, the collapse principle, if we try and actually see which slit the electron goes through, then the entire state collapses and you no longer get this quantum effect. You don't get this interference pattern anymore. Okay, so that's the double slit experiment, and it's one of the best pieces of evidence we have as far as I'm aware that quantum mechanics really does have this superposition effect. Okay, so that's all I want to say about quantum mechanics per se. How do we use it to compute? So again, this is supposed to be a very high level talk, so here's the very, very rough idea. So because I can put my quantum computer into two states at once, so I can put the input into both 0 and 1, then if I denote the answer for input 0 as A0 and the answer for input 1 as A1, then in principle, if I feed it a superposition of inputs and I run the computer just once, then I get two answers in one shot, okay, in superposition. I get the answer for 0 and the answer for 1. Okay, so does this mean that I've computed two things for the price of one? Think about this for a second. What have we just talked about, right, that seemingly is going to be a problem? If I want to extract an actual answer from my computation, well, I have to actually look at my quantum state, right? I have to observe it. And remember that the moment I observe it, I collapse the state. And what happens when I do a collapse? Well, at random, I get either A0 or A1, not both. Okay, I have realistically no control over this. And of course, once I see one answer, the other one's essentially lost forever. I would have to redo the entire computation to pick up the other one. Okay, so in this sense, we don't get anything for free in some sense. Okay, so that's really the basics of quantum computation. We try and compute things in parallel, if you will, quote unquote. And but the problem is we cannot extract all the answers at once. So the real challenge of the field is, well, how do you extract meaningful information from this superposition without completely destroying it, right? So it's like we're this cat over here, and the delicate superposition is this mouse, right? We're trying not to scare it off. And, it turns out that if you're clever, there are very subtle ways in which you can cause interference to happen in just the right way so that you amplify kind of the success probability or the probability that the answer you want comes out, okay? But that's about the extent of what I'll be able to say in this very high-level video. Okay, so that's all I want to say about the theory behind them, behind quantum computers, and now let me tell you a bit about applications. So in terms of kind of like the grand achievements, if you will, quote unquote, the most famous one is undoubtedly the factoring problem, right? This is important again because it will allow us to break certain crypto systems, indeed the most popular ones. The other most famous problem is perhaps this unstructured database problem, right? So what is the unstructured database problem? Let me just briefly tell you about this. Well, imagine you have a very, very big chest of drawers. Okay, so suppose you have a chest of drawers that contains 100 drawers, and in that drawer there is your lucky sock. In one of those drawers there's your lucky sock. And you're trying to figure out which drawer contains that lucky sock. You have no idea which one it's in. In a classical world, in the worst case, you would have to open every single of those 100 drawers to find your lucky sock. In a quantum world, it turns out that, roughly speaking, you don't need to check all 100 drawers. It suffices to check about 10 drawers, okay? So, I'm going to wave my hands here. For this unstructured search problem, you will get a square root speed up, basically. The square root of 100 is 10, over the brute force algorithm, which just checks everything. Okay, and there are some other algorithms that have since become kind of celebrated results, I would say, at least in my opinion, and I think that's probably fair to say in general. So for example, solving linear systems of equations, if you work in any type of, say, engineering field, for example, you certainly work with these all the time. And there we can get exponential speedups. And, for these three, I really want to be clear. Okay, so for factoring, we have a solution to the problem. But for these ones, these have an asterisk because you have to be very careful about the specific model that these problems are phrased in. Okay, and what are the assumptions that go into these algorithms? Okay, so for example, unstructured search is in the so-called black box model. Okay, so you have to be a little bit careful about how you interpret these results. Okay, but that's all I want to say. So there are some very nice algorithms in the quantum setting, but actually, I'm going to argue later on that even these algorithms are in some sense not, at least in my opinion, the most important application of quantum computers. Okay, others may well disagree, of course, and that's quite fine, right? Okay, but since we're talking about algorithms, let me just briefly say that quantum computers can do some great things in theory, at least, but there are also some things that we believe they cannot do. So, factoring is a very special problem. Okay, it's one of the few natural problems we know is of so-called intermediate difficulty, meaning, we can't solve it classically efficiently yet, but we also can't prove it's hard in any rigorous sense. Okay? And there is, however, another set of problems known as the NP-complete problems. And these are really notoriously hard. These are provably hard, up to standard conjectures. And it is these problems that we really do believe that quantum computers cannot solve, efficiently. So let me give you an example of a very famous NP-hard problem that is quite well motivated. So imagine that you are a salesperson and you sell some object, okay? So maybe you sell Tupperware, let's say, I don't know, right? And you want to visit all the cities in your country. But of course, you're trying to be cost efficient, right? You don't want to take expensive routes. You want to make the cheapest tour of all these cities. You never want to visit a city more than once. And you want to end up at the city you started with, the city you live in, right? So how can you compute the cheapest tour? That turns out to be essentially impossible, in the sense that if the map I give you is large enough, then it would take you longer to compute the answer on the best computers we have than your lifetime, basically. Okay? And these are the NP-complete problems. This traveling salesman problem that I just told you about, that is one of the standard examples. There are entire books written about it. And we don't believe that quantum computers can solve these efficiently. But let me be clear that there was a time, especially after the factoring algorithm broke, news of that broke, that very serious researchers in the field really put forth serious efforts to try and solve NP-complete problems using quantum computers. And nowadays, it seems like these techniques don't, unfortunately, quite work. Okay? So the point of this slide is that although quantum computers seem to be able to do some very good things like factoring, they certainly cannot do everything either. Good. So let me give you a second primary application of quantum cryptography, and this in particular is an application that you can take part in right now in some sense. And I'll tell you what I mean in a second. Okay, so really the first instance or suggestion of using quantum information for a computational task dates back to the 1970s. It dates back to Stephen Wiesner, who suggested this notion of so-called quantum money. And here the idea is that you can have a banknote, a quantum banknote, that would be essentially unforgeable. Okay, and how does this basically work? It works based on this principle, roughly speaking, that in a quantum world, you cannot just copy objects. Okay, so I can create a perfect copy of this pen more or less if I wanted to classically, but quantumly, you cannot do that with quantum particles in general. Okay, and so obviously that would make you think of something like a quantum banknote. Okay, and this idea was later, I think, generalized and certainly built upon very nicely in this very famous work of Bennett and Broussard for quantum key distribution. Okay, so in quantum key distribution, you imagine you have two parties. They want to share secret information, and before they do that, they want to first establish a secret key with which they can encrypt data. And using quantum mechanics, you can do this. And not only can you do this, but you can do it in such a way that it's provably secure up to the laws of quantum mechanics. Okay, so there's no assumption here other than you believe that quantum mechanics is correct. Okay? So the only way to break the scheme would be to violate the laws of quantum mechanics. And let me be clear that we don't have general purpose quantum computers at a large scale yet, but we do have special purposes devices. And by we, I don't mean we, as in me, of course, I mean companies such as ID Quantique here. Here's a snapshot of one of their web pages. They've been building these quantum key distribution devices for at least a decade now. Okay, so they're experts at it. You can go buy one if you want. Okay? So that's the second application, cryptography. Now, I want to talk about what, at least I consider, the most important potential application of quantum computers, which is the simulation of physical systems. Okay, so here's an old quote by Richard Feynman again. He says, "Nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. By golly, it's a wonderful problem because it doesn't look so easy." Okay, so in some sense, this was the original motivation, at least as far as someone like Feynman was concerned, one of the early proponents of quantum computing, for building these things. Okay, so what's the problem here? The problem here is that just to describe a set of quantum particles requires an exponential overhead in space. Okay, so if I had, say, n quantum particles I wanted to describe the state of, I would need 2 to the power n bits of information to describe that. So if you're not comfortable with that, what I just said, basically, as the size of a system, quantum system grows, the amount of space you would need to even just write down the state of that system would grow so quickly it would outnumber the number of atoms in the universe before long. Okay, so really it's infeasible. We can't even write descriptions of these things down. Okay, so the obvious thing, of course, here is that we cannot classically describe these systems, but at least there seems to be hope that perhaps you could use a quantum system to study another quantum system, right? In other words, you can use a quantum computer. That might actually have some hope in studying other quantum systems. And this is super important. Why is it important? Well, if you want to do things like design nanomaterials, you want to design medical drugs, you want to understand what's happening at that microscopic level, right? You need to understand how physical systems work. And if you don't believe me, that's fine. You should be questioning the scientific process, right? That's how the scientific process works. So here's just a screenshot I took off of Wikipedia. This is the page for supercomputers. And this table lists some of the primary uses for supercomputers in various decades. You'll see that in the 1970s, we focused on things like weather forecasting. But right now, in this decade, we focus primarily on molecular dynamics simulation, okay? Simulation of physical systems. That's what most of the world's supercomputers are doing, okay? Because it really is that important. Okay, so this is arguably one of the most important, if not the most important potential application of quantum computers. Okay, so that's all I want to say about applications, and now let's move to the last stage, experimental realizations / the race for so-called quantum supremacy. And again, I'm a computer scientist, and I'm in particular a theoretical computer scientist, so I don't build these devices. So this is the part I know least about, but let me try and share a little bit with you a bit about what I do know. Okay? So most of this information you could find online quite easily. So there are kind of different aims you could have, right? The question is, what is your target, right? So of course, in an ideal world, what we would have is the quantum analog of, say, your laptop, okay? A universal quantum computer that, in principle, you could feed it kind of whatever quantum software you want, and it would run the software, right? And in terms of building such quantum computers, there are a number of approaches for doing so. Let me just mention two here. One of them is ion traps. Okay, and so for example, there's a company out in Maryland called IonQ that specializes in this. And here, roughly speaking, at least at the beginning of 2019-ish, the scale we're looking at is these computers seem to be around 70 to 160 qubits in size. Okay. The other major framework is something called superconducting qubits. And here you have some other players like Google, IBM, Intel, and there you're looking at around 50 to 70 qubits. Okay. And my understanding is that both these technologies are not necessarily new. I mean, they've kind of been around for at least 1 or 2 decades now. And the one thing I really want to point out on this slide is that I can throw up all the qubit numbers I want here, like so 70 up to 160 or 70 to 5049 here. But really, what should you know as a public audience member? Well, qubit numbers are not everything. Okay, so the next time you see an article on quantum computing, you should ask yourself, well, there are two other very important metrics, at least, that we actually worry a lot about in the field, right? And I told you that quantum superposition is extremely fragile, okay? Any sort of noise will very easily destroy your experiment. And this is true not just if you introduce that noise, but even if the environment leaks noise into your system, okay? So it's very important that, number one, we worry about, how accurately are operations being performed? Okay, what are the operation fidelities? And number two, how long can you make your quantum state even survive before it just completely breaks down? Okay, before that fragile superposition is destroyed. That's the notion of coherence times. Okay, so qubit numbers are important, but just as important are these other metrics as well. Okay, so in other words, we also care about quality a lot, right? And this is really one of the challenging parts. Okay? And let me be clear that just as any scientific process goes, there's always back and forth, right? So on the one hand, you have these teams that are building physical quantum devices. On the other hand, you have classical teams, if you will, that are simulating those same quantum circuits classically and saying, aha, I don't believe you've built something that's generally better than a classical computer because I can still simulate your quantum device with my classical machine. So here's an example. In 2017, IBM classically simulated roughly 50 qubit short depth circuits. And they did it using, a computer of roughly this size. And so really the point I want to make on this slide is that really, we're at a very early stage, I would say, in the development of quantum computers, meaning in some sense you should think back like 100 years to these giant vacuum tube computers and so forth that were really just big babies in some sense, right? And that's in some sense where I like to think of where quantum computing is nowadays. Okay, there's a lot of amazing progress happening, but at the same time, of course, there's a lot to be done. And what's a lot of fun, I think, is IBM has been a good sport. They have this lovely IBM Q experience up. You can just Google it and find it. And essentially, you can interact with a real quantum computer. Well, maybe I shouldn't put quotes because from what I know, it's actually a real quantum computer. There's an interface and you can send it a circuit and it will simulate the circuit for you. Okay. So in terms of universal quantum computers, there's certainly some lovely progress, and at the same time, there's a lot to be done. So in the meantime, we can ask about the short term, right? And in particular, what's happened over the last few years there's been a push for something known as quantum supremacy. Okay, so what does this mean? This means that we ask the question, in the short term, can we build a quantum device, run an actual experiment in which a quantum computer, in some sense, provably outperforms the best classical computer? And let me emphasize here that what does it mean to outperform? Well, or at least what task is it going to be on? Well, I'm not going to care about the precise task itself. It could be a completely silly, useless task, but that's not the point. The point of this experiment is a proof of concept. Can you give me something at which you can prove to me a quantum computer does better? Okay, so indeed, so this is the so-called race for quantum supremacy, all right? Meaning that we want to come up with a task at which a noisy, intermediate scale quantum device, okay, so not a large one necessarily, can beat a classical computer in a near-term experiment that we actually run, okay? And there are various frameworks that one can try to show such a quantum supremacy result. Two of the ones that I'll mention here are so-called boson sampling and random circuit sampling. So boson sampling is arguably one of the simpler ones in the sense that it's trying not even to go into the general framework of quantum computing, but to stick to at least a conceivably simpler framework, which is just optics, okay? Just what boson sampling is about is this very basic idea. The task is this: you set up a bunch of mirrors, you shoot a light in, say a laser, and you try and predict where the photons are going to come out of your system of mirrors. That's boson sampling, right? And up to conjecture, we actually do have proofs, we as a field do have proofs that this task should be hard for a classical computer. Okay, but there's hope that a quantum computer can do it. The other major framework that I'll mention is random circuit sampling, and here what you do is pick your favorite random quantum circuit, so just randomly flip some coins and pick some gates, and try and simulate that, okay? And again, we have proofs that suggest this is going to be hard to do classically, but for example, if you followed the quantum news at all in the last few months, Google put out a research paper in the journal Nature that showed that they did a random circuit sampling experiment on roughly 50 qubits, okay, on an actual quantum device. Okay, and just as I showed before on the slide where we had this tennis game back and forth, indeed, that tennis game is very much going on. So on the one hand, you have Google saying, we did this actual experiment, we did random circuit sampling, and IBM pushes back now and says, well, that's a very nice experiment, but we believe that, the classical supercomputers we have, actually, if they're optimized right, we can actually simulate your quantum experiment on a classical device in a sufficiently short amount of time. Okay, so this is the scientific process in action, right? It's exactly what should happen. So very nice results on both ends, and hopefully it will continue to go forward. And that brings me to my summary. Okay, so we've said that quantum computers can theoretically outperform classical ones. And the main way we do this, roughly speaking, is that we exploit the fact that a qubit or a quantum particle can be in multiple states at the same time. In terms of applications, we've talked about algorithms like factoring. We've talked about cryptography and physical systems, which I argued is arguably the most important application. In terms of experimental applications, implementations of universal quantum computers, meaning general purpose ones, the rough ballpark, you should think about is maybe around 50 to 70. And like I said, there's been a very heated global race to demonstrate near-term quantum supremacy for non-universal quantum devices, and this includes this Google example I mentioned on the previous slide. So if you like this talk and you'd like to get a flavor for some of the research that's going on in the field, you can do that. You can go to archive.org, okay? And this is basically like the quantum analog of a newspaper, if you will, in the sense that every morning, if you go to this address, you will see the latest research papers get posted there, basically. And this repository is open access. Anybody can read these papers or download them. And there's a real sense in which this is very important, right? Because ultimately, we as a field, just like any other scientific field, owe you a debt of gratitude, because ultimately it is our tax dollars as society that funds these science funding agencies that promote the research that we do as a field. Okay, so thank you very much for your continued support, of course, and thank you for watching this video. Hope you enjoyed it. If you have any questions, please feel free to put them at the bottom in the comment section, and I'll try and get around to answering them. If there's a particular topic you want to hear about, if enough people bug me, then I might hopefully get some time together to actually put up a video on it. And finally, if you like the video, of course, feel free to share with whoever you think it might be appropriate for. Okay, thanks very much, and have a good one.